Hi, you this is Mr. Lim again, and this is the first of our bonus WACE exam questions. This is the 2017 WACE exam. So, here we have a question about isomers of C5H8O2. So you should recognize that all you got to do, since they're giving you those things here, all you got to do is count out how many C's, how many H's, how many O's. You should be able to do that. You should be able to count because, counting is good. And you should be able to see that C is the answer. Not that hard. It's just about counting. Please be able to count. Okay, which is following is the dominant form of glycine in basic solution. So again, this is about zwitterions and amphoteric nature. So in basic solution, there'll be lots of OH minuses floating around, ready to accept a proton. Okay, so therefore, the zwitterion is going to be in its, it's going to have to donate its proton to these things here. Right, so which one has donated its proton from the zwitterion form? This one is in fact the zwitterion form, so it's not that one. Which one is the one with one less proton? It's this one here, B. All right. So remember, in basic solution, there's lots of OH minuses. Zwitterions donate protons. In acidic solution, there's lots of H3O pluses, and therefore the zwitterion will accept protons. Okay. Again, identification, which one of these things, so remember that all of the organics are pungent, all right? We just need to work out what things are. Okay, add acidified potassium dichromate. What's that one do? That's oxidation. Okay, so does it oxidize? Yes, it does. Does it burn? Yes, it does. All right, that's combustion, which I mean all things do anyway, so their combustion. Add sodium metal. Metal reacts, colorless, odorless gas evolves. That is the reduction reaction, so that's a yes. And when added to acetic acid, it produces a fruity odor, which means that it's esterification. And remember, because you added it to a carboxylic acid, it means that this thing must be an alcohol. All right, and alcohols also oxidize, so therefore it's probably a primary or a secondary alcohol. And alcohols will also be will reduce sodium metal. All right, so let's move on. Which one of these represents a zwitterion? So remember, zwitterion, two charges on the same molecule, and you should recognize that this one and this one have two charges, but this one looks stupid, right? So it is A. All right, that's just something that you should recognize from zwitterion structures. Okay, you shouldn't see ever an OH2 or an NH minus. That looks silly. All right. Okay, now we get on to the short answers. Now, again, look at this. This is from Year 11 Organics. Okay, and so Year 11 Organics is kind of important. You are going to need to make sure that you remember stuff. The examiner's note says that lots of kids don't know the color of bromine water, which is not useful. Bromine water is orange. Okay, so identify excess propane gas. And so remember, it's important to remember what color or which one is in excess. In case excess propane gas was bubbled through an aqueous bromine solution, which means that you're going to have no bromine by the end of it, because it's all going to add to the propane gas. Identify by name or formula of the new substance produced. Okay, so propene. Here's your propene. All right. You're going to break the double bond with the bromine and add the two bromines there. So it's going to be 1,2-dibromo propane. So 1,2-dibromo propane. Okay. Write descriptions of the substances before and after mixture. Okay, so propane or any of these gases are going to be a colorless gas. Colorless gas. Okay. And an orange solution. And if you don't remember what color it is, that's fine. It is on the data sheet, but you have to make sure that you're looking at the aqueous bromine or the bromine in water, not the bromine in solid or bromine in the organic solvent. Okay, and what color is it after? It's just going to be a colorless solution, because all of the orange bromine will be gone because it's the limiting reagent compared to the propane gas. Okay, so it's just going to be a colorless solution, and it's going to be a colorless gas because this stuff there is there. You don't really need to give the color of the 1,2-dibromopropane. Okay, let's have a look at here. Alcohols and their physical properties. Ethanol and methanol are completely miscible in water, which means they're soluble in water by referring to any intermolecular forces present. Describe the dissolving process as ethanol is added to water. Now, you could have this this dissolving process described in 3 marks, or you could have it described in 8 marks or 6 marks, but you need to really make sure that you are just giving all the detail that you can. So, okay, so the report says, oh, that doesn't make sense, the any. Apparently might have inferred to discuss, oh yeah, that's right. So, in the question, it does say any, but you did need to respond to all of the van der Waals forces. So you got to write about them all. So why are they completely miscible in water? Always discuss all. What do we say about this? So, what happens in the dissolving process? So something about solvent bonds breaking, which is your well, actually not breaking, must be broken, because you must be answering the question. Broken. Solvent bonds must be broken, and that happens to be your dispersion, dipole, and H bonding. In an exam, you can't abbreviate like I can, but I'm just showing you what you need to do. Solute bonds must be broken. Ditto. What type of bonding do they have? They have, again, ditto. Dispersion, dipole, and hydrogen bonding. All right. That's the ethanol and the methanol. And so therefore the solvent-solute bonds formed, which are the dispersion, dipole, and H bonding, provide sufficient energy to disrupt the solute, and solvent bonds. Okay, the main ideas are to provide the sufficient energy from the bonds formed, right, to disrupt the bonds being broken. Okay, and then you must also have the listed types of van der Waals forces. Those were the 3 major marks. Right, let's move on. Alcohols and their physical properties. Why does the solubility of alcohols in water as the hydrocarbon length increases? So, number 1, you've got to state what it is. Okay, so solubility decreases as chain length increases. Okay, why is that? Okay, so it's going to create larger areas of dispersion, only forces around the thing, only forces around hydrocarbon tail or hydrocarbon end. Okay, and therefore the H bonding insufficient energy produced to disrupt the dispersion forces as they get larger. Okay, that's the idea. Have a look at the alcohol's physical properties. The idea is that, okay, you're going to have a larger area of dispersion forces or more dispersion forces around the non-alcohol end, right? Make sure that you state the relationship, and therefore it's insufficient energy produced. Okay, so it's always about the energy produced by the solute-solvent bonds being formed and whether they are sufficient or not, and make sure that you are answering the question by giving the relationship and then maybe explaining why. All right, let's move on. Aldehydes and carboxylic acids and their physical properties. This average was low, so kind of forget about dispersion forces. Even ionic substances will have dispersion forces, and the ions of a carboxylate will have ion dipole bonds. Okay, so for each of the following substances, list all of the forces of attraction formed between the solute and the solvent when dissolved in water. Okay, so this one here, propanol, it's an aldehyde, so therefore you're going to have H bonding, but it's talking about all of them, so you're going to have dipole and dispersion. Okay, methanoic acid, right? You're going to have H bonding, you're going to have dipole, you're going to have dispersion forces. Now this one here was a bit weird. It also had ion dipole, and that's the idea, is that when you have methanoic acid, you're going to have methanoate ions present, and that's a weird way to draw methanoate ions. And those methanoate ions are going to have a negative charge, and they're going to attract the positive end of the water molecules to that charge, and so therefore they're going to have ion dipole bonding. I would have thought that methanoic acid didn't have ion dipole, but that's apparently what the answer says, so go figure. Right, it's just that idea of the carboxylate ion will have ion dipole bonding. Right, and then sodium chloride. Right, many kids just wrote ionic. Unfortunately, you've forgotten that dispersion exists for everything. All right, so dispersion forces will also exist, and so therefore it's ionic and dispersion. Let's move. Draw one chain isomer for C5H10 that satisfies each of the following types. Right, this is about year 11 geometric isomerism because it's asking for cis and trans. Just another note, this one was talking about cyclic C5H10 earlier in the question. Okay, so cyclic C5H10 is a cycloalkane, so it acts like an alkane. And so therefore a chain isomer of C5H10 is going to act very different to the cycloisomer, because it is effectively going to have to be a alkene, because C5H10 is the CN and H2N formula, which is what for alkenes, for chains. Okay, so a trans isomer of that, as I suggest, always draw out the double bond first, draw out the 4 lines, and then work out what everything can be. Trans just means that they're going to be across. I know that there's going to be H's there, and then I'm just going to make it of variable lengths. So this can be CH3, CH2, CH3. Right, so remember when you're drawing structural formulas, you got to make sure that the bond goes to the atom that it's pointing at. So therefore that CH3 has to be written backwards as HC3. Okay, and then the cis isomer, where they're on the same side. Okay, CH2, CH3. Okay, so most kids apparently remember geometric isomers. Hopefully you will too. Right. Chemical tests can be used to distinguish between chain and cyclic isomers, again, because this is going to be an alkene and this is going to be an alkane. So what chemical tests can you do? You can react it to a bromine. Hey, we did that before at some point. Okay, so react with halogen. Okay, and the colors of the halogen will show. Okay, so react with some sort of halogen like chlorine water, or you can do bromine water, whichever one is closer and handy by. All right. And the observations expected for any reaction with each isomer. Okay, so this one here, the halogen water, whatever color you're going to be, whether it's a yellow or orange, turns to colorless. Okay, and you should have the Cl2 or the Br2 in limiting reagent, or as the limiting reagent, because you want it to become colorless. All right, or you can say that it's the excess of the chain or cyclic isomer. Now, you can't write no visible reaction for the cyclic isomer, even though that nothing happens. You're just going to have to say what it looks like. So whatever the halogen water color was, whether it was yellow or orange, it's going to stay yellow/orange, whichever one you've chosen as the chlorine or the bromine water. Okay, so that's important to remember. You just can't write down no visible reaction for that observation. You might as well just say what it is before and what it is after, and that's the same thing. All right, caffeine here. You can go watch the empirical formula videos. It's C4H5N2O. You work it out yourself, right? The molar mass of caffeine, you can watch that other video. Apparently, it's 194 grams per mole, and therefore it's double the empirical formula. Okay, that's the answer. You work it out. Now, this one here, last one. It was a cystic acid, which is an amino acid. Circle and label any functional groups as acidic or basic. So where are the functional groups? Here's a functional group. Here's a functional group. Right? Please make sure that you recognize that that's not a functional group. It's the whole thing that's a functional group. It's the carboxylic acid group. And here is a hypervalent sulfonate group. All right? Or maybe it's a sulfonite group, considering this SO3. You have to work out whether these are acidic or basic. That is acidic. You should recognize that from the carboxylic acid. This is basic because it's an amine. And this one here is acidic. Okay, how do you know it's acidic? These double bonded O's can't take on oxygens like the single bonded O can. All right, so therefore it's not going to. And there's a hydrogen to lose, so therefore it's acidic. Okay, that's it for the 2017 WACE exam. Just a little bit of stuff for you to go through. And if you have any questions, ask in class. Adios.